Alright, so till the last lecture we looked at extended surfaces on Cartesian coordinates where the cross sectional area of heat transport does not change. Now if you remember the discussion we had in the last lecture, in order to improve the heat transport, the ways by which we can do that is by increasing the heat transfer coefficient, cross sectional area, convective area of heat transport, and the temperature difference. So today what we are going to see is we are going to build upon that, and we are going to see how to quantify the increase in this convective surface area in a radial system. That is, we are going to look at fins in radial system. So what you see here is essentially the cut open of a cylinder with a fin which is placed around the cylinder. Okay, so it's in the outer rim of the cylinder. In principle, you can have multiple such fins, but let us first look at one fin. Okay, so now here is the cross sectional view or top view. Okay, supposing if the outer radius of the base cylinder that we are looking at, that is R1, and let us say the outer radius of the fin that you are considering is, let us say, capital R, and so the location can be described as heat transfer occurring along the top and the bottom edge of the fin, and let us say that we are trying to write a model to characterize the balance at any position R. Okay. Supposing if the thickness of the fin is T, then what is the cross sectional area of heat transport? What is the cross sectional area of heat transport? Okay, so it will be at any location R, the cross sectional area of heat transport will be the perimeter multiplied by the thickness of the fin. So the perimeter at that location is 2 pi R multiplied by T. So that is the cross sectional area of heat transport via conduction. Therefore, dAc by dC, dAc by dR is given by 2 pi into T. What is the area of heat transport via convection? So let us say I call this S, the surface area of heat transport via convection. So that will be this total area around the top surface plus the shaded area on the bottom surface of the fin, because the convective mode of heat transport is going to occur from both the top and the bottom of the fin. Okay. So therefore, the area would be 2 pi R square minus R1 square. So the radius of that location is R, and the radius of the place of the outer rim of the base is r1. Therefore, the net area of heat transport in the top surface is pi r square minus r1 square, but because there is heat transport from the top and the bottom, you have to multiply by 2. So, dAs by dr is given by 4 pi r. Okay. So, once we know these areas, we know the general model equation for such a fin. So, we should be able to plug these in and find the model. Okay. So, what is the general model? D square T by dr square plus 1 by AC, which is a function of position, into dAc by dr into dt by dr equal to h by kac into das by dr into t minus t infinity, where T infinity is the temperature of the surrounding fluid. So, now we can plug in these quantities. So, it will be d square T by dr square plus 1 by 2 pi RT, dAc by dr is 2 pi T into dt by dr, that is equal to h divided by k into 2 pi RT into 4 pi r into t minus t infinity. Okay. Okay, so we can rewrite this as d square. So, I can just cancel all the terms and it will be d square T by dr square plus 1 by r dt by dr, that is equal to 2h by kt into t minus t infinity. Okay. So, this model equation completely describes the heat transport via thermal diffusion in the fin and the convection from the top and the bottom surfaces. So, the first term, the left hand side term, captures the thermal diffusion of heat in the fin, and the right hand side captures the heat transport via convection from the top and the bottom of the fin. The boundary condition. So, if Tb is the base temperature, so T at R equal to R1 is Tb, and if I say I impose an adiabatic boundary condition, okay, adiabatic, I could in principle put a non-adiabatic, any of those 4 boundary conditions that we listed yesterday, you could in principle pose any of those 4 boundary conditions. So, let us say that we put the second case of no flux or adiabatic boundary condition. And so, we can solve this equation. What will be the nature of the eigenfunctions of this problem? It is an eigenvalue problem, as you can see in radial coordinates. J. Okay, what are the other? It is not J. What are the other eigenfunctions in radial coordinates? What are the distinct eigenfunctions in radial coordinates? R to the power of something is 1. No. It is a summation. It has to be a series summation. There are 4 types. Okay. There is J, there is Y, there is I, and there is K. These are the 4 distinct types. So, depending upon the forcing function that you have, you get different types of eigenfunctions. So, for this type of problem, the eigenfunctions are basically I and K. So, I will define in a moment what M is. So, these are the 2 eigenfunctions for this equation, and these are called as Bessel functions, if you know. These are called as Bessel functions. So, these are called as the Bessel equations. So you can write this in the form of Bessel equations, and that will be the eigenfunctions for the Bessel equation. So how to get these? We make a substitution very similar to what we did in the last lecture. So we say theta equal to t minus t infinity, and you say m square is 2h by kt. So we can transform these equations into d square theta by dr square plus 1 by r d theta by dr, that is equal to m square theta, and the boundary conditions will be theta at r equal to r1 will be theta b, and d theta by dr at r equal to capital R will be 0. So I am not going to derive the solution. You should derive this and convince yourself. So I will give you the solution. mr k1 mr2 plus k0 mr into I1 mr2 divided by I0 mr1 k1 mr2 plus k0 mr1, oops, that should be capital R, sorry, into I1 mr. So R is the outer radius of the fin, and so that is the solution. And just like what we did in the last lecture, one could derive what is the net heat transfer, total heat that is transferred by the fin. So note that when you want to quantify the processes occurring in the fin, you want to find what is the total heat transfer rate. Yes, I and j are the Bessel functions. There are 4 Bessel functions. These are called the first kind, and j is the 0 kind. There are 4 Bessel functions, j and y. Supposing if you have a modified, so there are 2 types of Bessel equations. One is the regular equation, the other one is the modified. Supposing if you have m square minus lambda square, you have 2 eigenvalue problems, then the solution you get is j and y. And when you have this kind of problem, what you get is I naught and k. So you should go back and read the Bessel equation solutions, and you will find this. For those who are interested to know more about Bessel functions, you should actually read the book. Maybe I will give you the reference. It is called Heat Conduction in Solids. Solids by Karsla and Ager. I think it was published in the mid 50s or early 60s. So this is by far like a golden standard for most of the problems that is dealt with in relationship with conduction, and you will see like exquisite presentation of all these Bessel functions, various kinds of solutions that will come about, and what are the different nature, what is the nature of different kinds of problems, and what is the nature of different kinds of solutions. So if some of you are interested, you should actually go and read this book. It's really very well written book, and I think it's and also quite lucidly presented. Okay, all right. So we said that we need to find the overall heat transport rate, and that is very simply given by, just like the way we did intuitively, we said that it's given by the dt by dr at r equal to r1. We said whatever heat that is transferred from the base is the total amount of heat that is transported through the fin. So based on that intuitive argument, we could find out what is the total heat transfer rate, and that is given by A 2 pi RT into theta B into M into K1 M R1 into I naught M capital R plus, So minus I1 MR1 K1 MR divided by K0 MR1 I0 MR I1 plus I0 MR1 into K1 M capital R. And similarly, one could find the fin efficiency, which is essentially defined as Qt by Q max. Qt by Q max. Q max is given by what's the maximum possible heat transfer rate? When can the fin achieve maximum possible heat transfer rate? When all of the fin is maintained at a constant temperature and that constant equal to the temperature of the base itself. So therefore, so that will be Qf divided by 2 pi R1 square minus R square minus R1 square multiplied by H into theta b. And so plug in all the expressions, it will be 2R divided by M R square minus R1 square, that into K1, this should be capital R, it is the total heat transfer rate. Note that it is a function of the total radius of the fin. Okay. So that will be K1 MR1 into 2 M capital R minus I1, it is the area, excuse me, thanks. So it is the area at the base, so it is R1, excuse me, minus MR1 into K1 M capital R divided by K0 MR1 I1 M capital R plus I0 MR1 into K1 M capital R. So that is the efficiency of the fin which is in the radial direction. So far we looked at only one fin. In fact, all the examples I told you, like the car radiator or the humidifying tower, they all have many fins, right? So what happens when there are many fins? So how do you find out the total heat transfer rate? Okay, so that is the question. See, ultimately what I want is, I want to find the total heat transfer rate. So if I have many fins and if I know what is the total heat transfer rate from one fin, and if I assume that all these fins are identical, which is typically the case, the geometry of all these fins are typically identical. So many fins, and if I say all have same geometry, okay. So if I assume that all the fins I have, they are of same geometry, then I could define something called an overall efficiency, okay, eta naught, which is the total heat that is transferred, that is the total amount of heat that is transferred divided by the maximum that is transferred by all the fins together. Okay. So supposing AT is the total area. Okay. So when I say total area, here I mean that area of all the fins plus area of the exposed base. Okay. So it might be useful to draw a picture now. So supposing, so this is the picture I drew when we discussed about when we initiated discussion about the fins. Okay. So supposing there are two fins, okay. So in principle the heat transfer is going to occur from the top bottom surface of the first fin. So if I mark this as 1, if I mark this as fin number 2, from top and bottom surface of the second fin, and from all the exposed area of the base itself, right. So the total area that is available for heat transport from a composite system like this, where you have many fins along with the base, would be area of all the fins which is available plus the area of the exposed base. Okay. So area of all the fins will be, supposing there are n fins which are present, then area of all the fins is n into area of individual fin plus the, let us say AB is the area of the base which is available for heat transport. Okay. So that is the area which is available in between, right. So those, that is the area of the base. So the total area which is available for heat transport is now given by n into AF plus AB. What is QT? What is QT? QT is the total amount of heat. So that will be n into QF. If QF is the total amount of heat that is transported by one fin to the fluid around, plus whatever is transported by the exposed base. Okay. So that we can write as n into h into area of the fin multiplied by theta b into eta f. So note that the efficiency of a single fin, right, let us mark it here. So efficiency of a single fin is simply given by QF divided by h into area of fin into theta b, right. So that is the definition of the efficiency of a single fin. So based on that definition, n into h AF theta b into eta f will be the total amount of heat that is transported by n fins together, plus whatever is the amount of heat that is transported by base, which is given by h into area into theta b according to Newton's law of cooling. So note that here theta I already account for the difference in the local temperature and the fluid temperature. That is the nomenclature that I have been using. Theta is essentially T minus T infinity. So the T infinity is the temperature of the fluid which is flowing around, and theta is T minus T infinity. So the total amount of heat that is transported by this composite system is n into h into AF theta b into eta f plus h AB into theta b. Okay. So now I plug all these here, be n into h into AF into theta b into eta f plus h into AB into theta b divided by Q max is h into the total area which is available, that is the composite area which is available, and if all the every location in the composite is maintained at a certain temperature which is equal to the base temperature and constant, so that will be the maximum heat that is transported by that composite system. So AB is given by A total minus n times the area of fin, simply from the conservation of the total amount of area. So substituting this, you will get eta naught is equal to n h AF theta b eta f plus h into A total minus f into theta b divided by h into A total into theta b. So we can do a simple algebraic rearrangement. So that will be, so this term will become 1, so it will be 1 plus n into AF by AT into eta f minus 1. So the efficiency of the composite system can now be easily expressed in terms of the efficiency of a single fin. So what it tells you is that if you are able to model and quantify the heat transport process in one fin, you are done. So you can easily find out what is the total heat transport rate from the composite system by simply multiplying. So QT is nothing but eta naught into Q max. By simply multiplying eta naught and Q max, you will be able to find out what is the total amount of heat that is transported by the composite system. Okay. So that is H AT theta B into 1 plus N into AF by AT into eta F minus 1. So what happens when N increases? Does the heat transport rate increase? From this expression, that's what you would intuitively guess, because that's what you want to achieve. By putting many fins, you want to increase the heat transfer rate. Does the expression also show that? By increasing N, does it increase the total amount of heat transfer rate? This is very important. Anytime you do such quantification calculation, you should always check whether what you predict is exactly what you intuitively would guess. Yes or no? Why? Eta F also, that's okay. Eta F is anyway a quantity which is less than 1. So it doesn't matter, no? So as long as you know eta F, let's say I know what is the efficiency of one fin, okay? Would the heat transfer rate increase if I duplicate the geometry of that fin in different locations? No, assume that all that is true. There's enough. Assume that the fin is always exposed with the liquid. Doesn't matter. So does the expression predict that the heat transport rate increases with increasing the number of fins? Eta F is less than 1. That's right. So note that this is the maximum, right? So as you increase N, what happens? Which one? So note that the AT is going to increase as you increase the number of fins. So it's not very obvious to see from this expression. So for various values of AT, so one has to actually, so as you increase the number of fins, keep in mind that AT is also increasing. So AT is not constant there. So it's not very obvious to see from this expression. So as you increase the number of fins, keep in mind that AT is also increasing. So AT is not constant there. So it's not very obvious to see from this expression. So for any specific system, the first thing you should do is, as you increase the heat transfer area by including multiple fins, you will have to make a plot of Qt versus the number of fins. So only if the Qt is going to increase with the number of fins, then it is worthwhile making such a construction. Otherwise it doesn't make any sense. So the first thing you should check is whether Qt for a given system, I mean it may not be linear, a simplistic expression is, supposing if the Qt increases linearly with respect to the number of fins that you are actually constructing in this complex system, only then it is worthwhile to put the number. In fact, that's how you set the number of fins that you should choose. What is the total number of fins that is going to maximize by my total amount of heat that is transported? If it's not going to maximize, then there's no point in doing that. It's a waste of money to put additional fins. It's very expensive. By the way, you must understand that machining and adding new components is not a cheap task. It's very expensive to do machining and add materials to an existing system. So there are lots of direct obvious costs, there are lots of hidden costs which is involved in these kinds of things. So it's very, very important to understand what should be the maximum number of fins that you should choose. And in fact, this is one of the important purposes of doing modeling. You must get a feel of what should be the maximum or optimum amount of heat that will be transferred depending upon the number of fins that you choose. Otherwise, you don't want to shut the plant to change this. So when you shut down the plant, supposing if there is a big plant which is running where there is a heat transfer equipment, if you want to change the design, you will have to shut down the plant. It costs a lot of money, indirect money, to shut down the plant. So it hits the economy a lot, economy of that particular process. So you really want to use these modeling to find out what is the optimal number. even before you attempt to make a construction. So this is an important aspect of the models that you would construct, not just this engineering class, but any other engineering system. This is one of the primary purposes of modeling. Okay, any questions?